So let's start as usual with some review of the previous class. So last time we classified Möbius transformations up to conjugation, and somehow the point is that we are somehow so lucky that many things fit together. Right? I mean, any Möbius transformation having only one fixed point, being infinity this fixed point, is automatically a translation. Every Möbius transformation having exactly two fixed points, if the two fixed points are precisely 0 and infinity, this Möbius transformation is multiplication by some non-zero complex number, right? And also different from 1. So that's one of the facts that fit together for us to be able to obtain the classification up to conjugation. The second fact is that every Möbius transformation different from the identity has either exactly one fixed point or exactly two fixed points. That's like the second fact that fits together. I mean, right? And then the third fact that fits together is that in the case of the standard examples, which is when the Möbius transformation has either exactly one fixed point and the fixed point is infinity, or exactly two fixed points and the two fixed points are 0 and infinity, that in the standard examples, it is very easy to find a family of curves consisting of curves, each of which is stable under all integral powers of the corresponding standard example, and the other transversal family that is permuted by the integral powers of the transformation. That's the third fact. And in the end, what we do is, given an arbitrary Möbius transformation different from the identity, we take the two fixed points, which, by the way, we can compute explicitly in terms of the entries of the matrix, and build and construct a Möbius transformation, sending the two fixed points, the two fixed points to 0 and infinity, if this were exactly two, or the unique fixed point to infinity if there was exactly one fixed point. And then we had this nice identity, which was this the fixed points on a set X of G, F, G inverse are exactly G of the fixed points, right? Because then what we just did was construct this G that sent the fixed points to 0 and infinity, or to just infinity if there was only one. And it turns out that what we obtain, that is 0 and infinity, are precisely the fixed points of this conjugation. Right? Hence, it's either a translation or a multiplication by some non-zero alpha, and that's the first theorem, right? The first proposition, which is every non-identity Möbius transformation is conjugate to a standard example. So the problem became classify all the standard examples up to conjugation. And so the first thing is Möbius transformations with exactly one fixed point and Möbius transformation with exactly two fixed points are never conjugate, right? I mean, one with exactly two fixed points is never conjugate to one with exactly one, right? So that's the first thing. So we can focus just on classifying those with exactly one and classifying those with exactly two. And in the case of exactly one, we saw that all translations are conjugate to each other in the Möbius group. So, and from there, the conclusion that we drew is that all Möbius transformations that have exactly one fixed point are conjugate to one another. They form exactly one conjugacy class in the Möbius group. And in the case of exactly two fixed points, we saw that multiplication by that the transformations given by multiplying by some non-zero complex number are conjugate if and only if the complex numbers involved, the complex numbers by which we multiply, are either equal or inverse to one another. Right? So in particular, multiplying by alpha and multiplying by alpha inverse are conjugate. And somehow the conjugation is kind of roughly speaking, corresponds to deciding, whether the fixed point 0 and infinity, whether we see them as the south and north pole in the sphere, or the other way around, right? by certain rotation of 180 degrees, which corresponds to 1 over z. Right? So that's the ambiguity between in this conjugate in this fact that it may be that multiplication by alpha and multiplication by alpha inverse are conjugate. All right, so we saw that, and then according to where, you see, once we know that Möbius transformation with exactly two fixed points is conjugate to multiplication by alpha and alpha inverse, where alpha and alpha inverse are kind of uniquely determined by the Möbius transformation with exactly two fixed points, and that if I change the alpha and alpha inverse to another pair of mutually inverse complex numbers, I actually change the conjugacy class. Once we know that, then we take our Möbius transformation with exactly two fixed points, and depending on where these two numbers, which I call the multipliers, lie, right? And the main the sets that I look at are the unit circle, the positive real numbers, and the rest. Right? And then I call the transformation elliptic, hyperbolic, and loxodromic accordingly. Then there was some sort of reminder about the conformality of Möbius transformations, and the point was to stress two facts. One is that conformal transformations between Riemann surfaces, or holomorphic transformations between Riemann surfaces, in particular, preserve the measure of angles, measures of directed angles between curves. Second, kind of to compute the generic value of the derivative of the derivative of a Möbius transformation at some point. I mean, at a generic point, and by generic I mean kind of one which is not exceptional in the sense that it is not infinity and its image is under the Möbius transformation is not infinity. Right, so we computed the derivative in that case, and then I left as an exercise to compute the derivative in the non-generic cases, right, where the point can go to infinity under the Möbius transformation, or it itself can be infinity. Right, kind of it's an exercise meant to test your understanding of the charts of C bar as a Riemann surface. Okay, and finally, we established the Steiner grid of a parabolic transformation, and the point is, a parabolic transformation is by definition a transformation that has exactly one fixed point, hence conjugate to a translation, and this translation is translation along some vector, and then we take the parallel lines to the vector, which are precisely the curves in C, which are not the curves, but they are curves in C bar, stable under the integral powers of the translation, and then we map them back through the inverse of the conjugating transformation to obtain a family of circles in C bar that are stable, each of which is stable under all the integral powers of my original parabolic transformation. Right? And then we did something similar with the orthogonal, with the lines that are orthogonal to the translating vector, right? And then we gave an exercise that what it says is, well, we know that a parabolic transformation is a parabolic transformation and any translation are always conjugate. So which one do you use? Right? So which translation do you use to map the corresponding lines? And then the exercise says, okay, you can use whichever you want. Right? So this, in other words, the final two families are well defined for my arbitrary parabolic transformation. And then the pair consisting of those families, we called it the Steiner grid, right? And then somehow in C bar, the picture is more or less this, where we agreed that somehow the orange circles represent the curves that are stable, right? And the red circles represent the curves that are permuted. And then we saw that because of what happens on the side of translations, in my arbitrary parabolic transformation, it happens that the behavior under applying let's say the positive powers of nu always goes kind of in one sense. Let's say here for this circle counterclockwise, and then it's kind of it's in the same sense like everywhere. And by this, what I mean is that somehow here, if I stand here close to the fixed point, somehow here I'm going to start getting away and then converge to it on the other side. That's what I mean. So for instance, here the behavior would be like this, etc. Right? By the way, for instance, for the inverse is also parabolic, and then it would go the other way around, of course, right? Okay, and that was it.